Very well, we are on chapter 3.1, the logic of quantified statements. Very well, here we have some statements and we're interested in writing them in the nicer format that we can actually analyze each of those statements. Officially, we define a predicate as a sentence that contains a finite number of variables like x, like y, just finite numbers of them, and becomes a statement. Remember that in logic, we said we have a statement if it is true or false, not both of them. When specific values are substituted for the variables. So for example, you can substitute 1, 2, 3, a half negative values for your x, y, or free variables. Then we define something that we call the domain. Then we define something that we call the domain of a predicate, which is the set of all values that may be substituted in the place of variable. Perfect. Let us go over one example to feel more comfortable about this topic. Suppose P of x is a predicate which says x squared is always greater than x. With domain set R, all real numbers. Question says write P of 2. It means that wherever we see x, we write 2. Then it says evaluate P of a half, then evaluate P of negative a half. So wherever we see x, we substitute these values. And finally, x, negative a half. And indicate which of these statements are true and which ones are false. Perfect. So we have a statement, x squared is greater than x. P of 2 says 2 squared is greater than 2, or 4 is greater than 2. So obviously it is always true. Next one, P of a half. A half squared is greater than a half, or a fourth is greater than a half. You know that this is a false statement. Then P of minus a half. Wherever we see x, we just substitute minus a half. Minus a half squared is greater than negative a half, or a positive number, a fourth, is greater than negative a half. Obviously, this is true. Very well. When an element in the domain of the variable of a non-variable predicate is substituted for the variable, the resulting statement is either true or false. So we can actually investigate if it's true or false. The set of all such elements that make the predicate true is called the truth set. The domain is R. Truth set is all numbers, all elements, all values that make the predicate a true statement. What is x squared greater than x? If you get back to algebra, x squared greater than x, or x squared minus x greater than 0. If you use your little table, 0 and 1. If you plug in any number greater than 1, like 2, it's positive. If you plug in any number less than 0, like -2, it's also positive. Any number in between, like a half, gives you negative sign. So you have a graph that passes through 0 and 1, and it behaves like this. Since you have a discrete function, you can just use dots. In this case, your domain is all real numbers, so you can connect all of these points together, and this is the graph of this function. X squared is greater than x. It means that you can just erase lower part of your graph. And we don't include the intersects. So the truth set is going to be all numbers greater than 1, all numbers less than 0 for this special case. Very well. So officially we say that the truth set of P of X is the set of. So the set of, remember that for a set, we use curly brackets. The set of all X values such that P of X is true, or it satisfies P of X. Another example. Suppose your goal is to find the truth set of a predicate. Suppose Q of n is a predicate which says that n is a factor of 8. N is a factor of 8. Find the truth set of this predicate given different domain. The first domain is all positive integers. The second domain is all integers. Perfect. So, first of all, what is a factor? Suppose you have 8. Factors of 8 are 1, 2, 4, and 8. What about negative values? Are negative values a factor of 8? Of course. 8, the factors of 8, let's use dots here. -1, -2, -4, -8. Why we say that these are factors? D is a factor of n if D divides n. D divides n. Like 2 divides 6. 6 is 2 times 3. 3 divides 6. 6 also divides 6. 1 divides 6, of course. 6 is 1 times 6. These are all factors of 8. You can consider positive values and negative values. Okay, let's take a look at the first domain. It's all positive integers, positive counting numbers, or just n, natural numbers. So the factors that you can consider are 1, 2, 4, and 8. So the truth set for all factors of 8 with this domain, positive domain, are the set of 1, 2, 4, and 8. What if we consider all integers, like z? Z includes all negative and positive counting numbers along with 0. Perfect. So we can list all of factors of 8, either positive or negative. Negative 1 divides 8, of course. Negative 2 divides 8, of course, because you can write 8 as negative 1 times negative 8. We can write 8 as negative 2 times negative 4. So these are all factors of 8. Very well, let us move on to the next page. Let's talk about universal and existential quantifier. So first of all, we define two quantifiers in this course. The first one is called universal quantifier, and the symbol that you use for it is upside down A. The second quantifier is called existential quantifier, backward E. When we are talking about universal quantifier, it means that it includes all elements, everything. When you're talking about existential quantifier, it means that there exists one element. So all versus one. So these quantifiers are used to give a more compact format of writing statements. For example, you can say there is one natural number such that 1 over that natural number is also a natural number. There exists an element of natural numbers like x such that its reciprocal 1 over x is also a natural number. Okay, can we find that number? Yes, if you consider x to be 1, the reciprocal of 1 is 1, which belongs to n. Remember, n is counting number. N, the set of all counting numbers. 1, 2, 3, 4, 5, and the rest of them. There is? Yes, there is. I found it. It's just right here. So this statement is true. This is a true statement. I just proved that statement by finding the element x equals to 1. Perfect. Next, for all, for any, for every real number, the square of that number is positive. Here you have a universal statement. You use a universal quantifier, and here's you have your domain, and this is your statement. So is this true? For any x belongs to R, x squared is always positive? Okay, what if I use 0? 0 is a real number. 0 squared is 0. Is this guy greater than 0? Of course not. I found one element that makes this statement false. So in general, this statement is false. Very well. Illogical conjunctions and disjunctions are related to our quantifiers. So the universal quantifier is related to a logical conjunction. For example, consider for any x in R, x squared is greater than equals to x is actually equivalent to saying that P of x, your statement, is true for any x in R. If you have existential quantifier, it's related to logical disjunction. For example, there is one x in R such that x plus 1 is equal to 0. Next up is universal statement and counterexample. So suppose you have a statement like Qx and the domain is D. Universal statement for all x in D, Qx is defined to be true if and only if this statement is true for any random value, any value. If I take that value, if you take that value, if another student take that value, is true. It's defined to be false if and only if you can find at least one element in the domain that make this statement false. We call that value that make a universal statement false to be a counterexample. For example, consider this statement: x squared is greater than equals to x when x belongs to this domain. The first domain is a countable domain, finite domain. X is 1, 1 squared is greater than 1. X is 2, 2 squared is greater than 2. X is 3, 3 squared is greater than 3. X is 4, 4 squared is greater than 4. X is 5, 5 squared is greater than 5. For each of these elements, for every element in the domain, we prove that this statement is true. So if you restrict yourself to this domain, this statement is true. What if I change my domain? What if I change the domain to be all real numbers? Of course, this statement is not going to be true anymore. Consider x to be a half. Then a fourth is not greater than equals to a half. So here we found a counterexample that makes this statement false. One is enough. You can use a third, you can use a fourth, anything that you like. It's not unique. Existential statement. So for existential statement, we use there is, there exists an element in the domain such that Qx, it's true if and only if Q of x is true for at least one element, in the domain. So remember that for universal statement to be true, it must be true for all elements in the domain. Existential statement, it just says find one element for me. That's enough for me. Then I'll be true. For example, suppose your statement, your existential statement says there is a positive integer such that m squared is equal to m. Can you find m? 1 is enough because it's an existential statement. So you can assume m equals to 1. I found one element that satisfies this relation. This one statement makes the existential statement a true statement. Now, what if I change my domain? I say domain is now 5, 6, 7, and 8. Can I find one element in this domain that makes this statement a true statement? I have to check each of them. Let us check 5. Is 5 squared equals to 5? Nope. 6 squared is equal to 6? Nope. 7 squared is equal to 7? Of course not. 8 squared is equal to x? 8? No, of course not. So in this domain, I cannot find one element. I checked all of them. None of them are working. So this statement is false in this domain. Guys, you need to be careful about the given domain. More examples. Rewrite the following formal statements as equivalent to statement in English. So the first one says, for any real number, its square is always greater than equal to 0. Okay, you can say that every real number has a non-negative square. You can also say that any real number has a non-negative square. You can also say that the square of each real number is non-negative. B, for any x in R, x squared is never -1. Remember that if you want this statement to be true, you have to change your domain to complex numbers. So we can read B, no real numbers have squares equal to -1. All real numbers have squares that are not equal to -1. C, there is a positive integer such that m squared is equal to m. Very well. There is a positive integer whose square is equal to itself. We can find at least one positive integer equal to its own square. Some positive integer equals to its own square. Some positive integers equal their own squares. Another example. Now suppose you have just some statements and you want to write them in mathematical format. The first one says all triangles have 3 sides. All, it's a universal statement for all, for any. Okay, first of all, you can just write it this way. For all triangles like T, you need a variable. T has 3 sides. For any random variable T, which in this case is a triangle, belongs to the collection of all triangles. Here you're defining a domain. T, or that variable, has 3 sides. 2 different ways to define A. B, no dogs have wings. No random dogs. So you can say that for any dogs like D, D does not have wings. Or you can first define a domain of all dogs. Then say that for any variable D in domain D, D doesn't have wings. Finally, some, remember that some, there exist. Some programs are structured. How do we write it in mathematical form? There is a program like P such that P is structured. Or again, you can define a domain and define a variable like P. There is P, variable P in domain P, such that P is satisfied being structured. Very well. So which quantifier do you use when they have a conditional statement? Biconditional statement. When you have a conditional statement, it's actually a universal statement. You're saying that for any x in the given domain, px implies qx. Px, then qx. So it's a universal quantifier. Also for biconditional statement, it is also a universal statement. None of these are existential statements. For example, suppose Qn says n is a factor of 8. Rn says n is a factor of 4. Suppose the domain is all positive integers. Use conditional statement to indicate a relation between Qn, Rn. So we either have to say that for any n in Z positive, Qn implies Rn, or we need to mention that for any positive integers, Rn implies Qn. So which one is correct in this case? Take a look at the factors of 8 in positive integers. It's 1, it includes 1, 2, 4, and 8. For 4, factors are 1, 2, 4. So if you say that Qn implies Rn, it means that if I take a random element in Qn, that element must be in Rn. So suppose I take 8 as a random element in Qn, the truth set of Qn. As you can see, 8 is not in the truth set of Rn. So this cannot be true because of 8. But its inverse is correct. If you take any random element in the truth set of Rn, that element for sure lands in the truth set of Qn. So for any n in positive integers in the domain, Rn implies Qn. Or the truth set of Rn is a subset of truth set of Qn. Perfect. Let us continue. The negation of universal statement, also the negation of existential statement. How do we negate these? So suppose you have a universal statement for any x in domain D, Qx. The negation of this statement is the negation of for all is there exists. So the negation of for all there exists, such that the negation of your original statement. So you're negating two things, the negation of the quantifier and the negation of the statement. Symbolically, we can write the negation of for any there exists and the negation of Qx not Qx. Example, write formal negations for the following statement. For any primes like P, P is odd. So you have prime numbers and you're saying that P is odd. The negation of for all there exists. The negation of P is odd. P is not odd. So the negation of for all there exists. The negation of is not. What if we have existential statement? As you guessed, the negation of there exists is for all. And of course, you have to negate the original statement. Or symbolically, we can write the negation of there is an element in the domain D such that that statement is going to be for any, for all x in domain D, not Q of x. So that's how we negate an existential statement. Very well. One example. It says there is a triangle like T such that the sum of the angles of T equals 200 degrees. Our goal is to negate this existential statement. The negation of there is going to be for all, for any triangles like T. The negation of the original statement, the sum of the angles of T does not equal 200. So equals, the negation of equals does not equal 200 degrees. Okay, critical thinking for you. What's the negation of universal conditional statement? Here you have the negation of for any x, if P, then Q. Remember that, recall, P, then Q is equivalent to not P or Q. Remember that to negate conditional statement, we cannot work with original format. We have to negate or. So here you have not for any x, not P or Q. So first we convert then into or, then we take the negation. Negation of for all is going to be there exists, such that negation of P double negation gives you Px. The negation of or is going to be and the negation of Q is not QX. That's the negation of conditional statement. For a conditional statement, it's always universal. Perfect. Now consider the statement of the form for any x in D, domain D, if Px, then Qx. Remember that the contrapositive is defined to be for any x in the domain D, if not Q, then not P. The converse is another universal statement for any x in D, if Q, then P, and its inverse for any x in D, if not P, then not Q. Guys, note that we didn't use negation on the original statement. I didn't negate the universal statement. I defined some new statements. These are new definitions. That's why we didn't change the quantifier. The quantifier stays the same. It's not the same as negation. Not the same as negation. Do not confuse these. Let's take a look at one example. Write a formal and informal contrapositive, converse and inverse for the following statement. It says if, so you see if, it means that you have a conditional statement. If a real number is greater than 2, then its square is greater than 4. So a formal version is written as if conditional for all. For any x in R, any real number R, if x is greater than 2, hypothesis, and conclusion, x squared is greater than 4. Let us define the contrapositive. You copy down your quantifier for any x in R. Now, the negation of x squared greater than 4 is x squared less than equal to 4. Then the negation of x greater than 2 is x less than equals to 2. Again, if you have P, then Q, contrapositive is not Q, then not P. The negation of conclusion implies the negation of hypothesis. Converse, take a look at the definition. All three definitions are up here. Converse, we just switch the conclusion and hypothesis. For any x in R, again, it's a universal statement. What was your conclusion? X squared greater than 2. Now it is your hypothesis. And your conclusion in the converse is the hypothesis in the original statement. Q, then P. And finally, the inverse, the negation of hypothesis, then the negation of conclusion. For any, again, we do not change the universal statement. For any x belongs to R, if x is not greater than 2, it means that x is less than equals to 2. Then you negate your conclusion. X squared is not greater than 4. It is less than equals to 4. That's how we form contrapositive, converse, and inverse of a universal conditional statement. Again, here's a note for you. X is not greater than A is the same as saying that X is less than equals to A. Very well. Translating multiply quantified statements from informal to formal language. First of all, let us define the reciprocal. The reciprocal of a real number like A is another real number like B, such that if you multiply those two numbers, the outcome is 1. Perfect. The following two statements are true. Rewrite them formally using quantifiers and variables. The first one says, every non-zero real number has a reciprocal. So if you take any random, as you guessed, it is for all. Any random non-zero real number, there is another real number such that their product is 1. For any non-zero real number like you can find a real number like V such that their product is 1. So we're using a combination of universal and existential quantifiers here. B, there is existential, a real number that has no reciprocal. There is a real number such that if you take any other random real number, their product is never 1. There is a real number like C such that for any real random number like D, their product is never 1. Both of these statements are true. Perfect. So how do we interpret statements with two different quantifiers? So if you want to establish the truth of statement of the form, for all x in D, there is y in E such that P of x and y. You're actually trying to see if someone else, another student, pick another element like x in D, then there is an element like y such that P of x and y is a statement that you can assign truth or falsity to it. But what if you have there is x in D such that for any random y in E, P of x and y, it means that your job is to find one x in D that works for any y in E. That's the difference between these two. Very well, I expect you to ask, what if I have 2, 3, or more quantifiers in a statement? How do I negate that? So you know that the negation of a universal statement, like for any x in D, Px is there is. So you are negating the universal quantifier and you get there exists, existential quantifier, and the negation of the original statement, not P. And if you have existential statement, the negation is for any, not P. But if you have both, there exists and for all in a statement. Very well. The negation of for any there exists. Now here you use two variables, p of x and y, is equivalent saying that there is, so the negation of for all is going to be there exists. The negation of there exists is going to be for all, and the negation of your original statement. What if we want to find the negation of there is for all p of x? In this case, you're negating each of them from left to right. The negation of there is for all. The negation of for all is there exists, and the negation of original statement is going to be not p of x and y.